Okay, let's dive right into this explainer and completely demystify that incredible microscopic factory running inside the black box sitting on your desk. Today, we're popping the hood on the system unit to see exactly what makes your computer tick.
It's a super simple action, right? You probably do it every single day. But what actually happens when you press that power button? To understand how your machine springs to life in just mere seconds, we've got to map out its internal anatomy. We're going to see how all these invisible processes become visible right there on your screen.
We're going to tour this system like it's a bustling metropolis. Here's our agenda. First, the system foundation. Second, brains of the operation. Third, memory versus storage. Fourth, highways and connections. And finally, number 5, the processing cycle.
All right, let's kick off our tour with Section 1, the system foundation, basically the overall city grid.
Taking a wide look at the layout, you can immediately spot the major departments of our digital factory. Up at the top, we've got the power supply unit. Spanning across the back is the massive motherboard foundation, and smack in the middle, working incredibly hard under a large cooling fan, are the processors. Off to the side, you'll find the bays housing all the secondary storage.
Let's pull out that motherboard for a closer look. The motherboard is literally the ultimate foundation of the whole system. It acts as the primary circuit board, serving as this critical platform that provides all the necessary slots and ports to connect absolutely every peripheral device and electrical component together. I mean, without this grid, none of our factory departments could even exist.
But, none of that beautiful circuitry actually matters without the power supply unit, or PSU. The PSU's job is crucial. It pulls in high-voltage alternating current from your wall outlet and converts it down to a safe, low-voltage, direct current for the components. And since doing this generates a massive amount of heat, nearby cooler fans and heat sinks are constantly working overtime to dissipate that heat so the whole system doesn't just melt down.
Moving right along to Section 2, brains of the operation. Let's meet the general manager.
This small, unbelievably complex chip is the central processing unit, the CPU. Think of it as the chief executive of the computer. It's responsible for processing all the data and instructions. And the speed at which this executive works, it's measured by its clock rate, which dictates exactly how many instructions it can process in a single second. And we're often talking in the billions here. Billions!
Now, while the CPU is the general manager, it is definitely smart enough to know when to delegate. For visually intensive tasks, it hands the heavy lifting off to the GPU, the graphics processing unit. Just think about how massive a dedicated graphics card is compared to the CPU. It's a highly specialized department loaded with way more cores, designed strictly for graphic rendering, executing complex commands, and heavy multitasking.
The trade-off designers face here is pretty fascinating. A dedicated graphics card gives you massive, high-end graphics processing power, which is absolutely essential if you're into gaming, 3D design, or video editing. On the flip side, an integrated GPU, which is built right directly into the motherboard or the CPU itself, offers a lower cost and much lower energy consumption. That makes it totally perfect for general word processing and your daily web browsing.
Okay, every factory needs places to put things, which brings us to Section 3, memory versus storage. The critical difference between short and long-term memory.
The key takeaway here is understanding main memory. Think of RAM, or random access memory, as a tiny, ultra-fast workbench. It holds data temporarily while the computer is actively processing it. But here's the catch. It is highly volatile. That means it forgets absolutely everything the second the lights go out. Contrast that with ROM, or read-only memory. ROM is non-volatile. It's the permanent instruction manual that stores firmware, ensuring your computer actually knows how to boot up in the first place.
Because RAM forgets everything when you power down, for long-term memory, we absolutely have to rely on secondary storage. These are your non-volatile warehouses. They keep your data safe even when the power is completely disconnected. We're talking about traditional hard disks with their spinning magnetic platters, much faster solid-state drives that have zero moving parts, and even those portable USB flash drives you carry around.
Depending on the need, our digital factory can use a few different storage architectures. You've got massive magnetic tapes, which are mostly used for long-term enterprise backups. You've got your hard disks and SSDs for direct everyday access. And for serious data safety, you can use RAID arrays, which combine multiple drives to prevent data loss if one happens to fail, or a NAS, network-attached storage, which basically acts as a localized file server for multiple users on a network.
So, how do all these separate parts talk to each other without causing total gridlock? Let's look at Section 4, Highways and Connections, focusing on the system buses.
To communicate, these components use system buses. You can think of these as multi-lane digital highways, specifically designed for transferring data and control signals back and forth between the processors, the storage devices, and your input/output devices. The physical width of these buses literally dictates how much data can flow at any one time.
Notice just how structured the traffic is on these highways. We essentially have three main types. The control bus carries signals that manage the system. That's a strict one-way street from the processor to the components. The address bus, which finds exactly where data lives in memory, is also a one-way street out from the processor. But the data bus, which carries the actual instructions and files, well, that gets a full two-way highway between the processors and components.
We even have specific off-ramps on our motherboard for different types of traffic. The SATA bus ports connect directly to secondary storage, like your hard drives and optical disks. Meanwhile, those longer PCI slots act as high-speed express lanes. They allow processors to transfer data at incredibly high speeds to heavy hitters like graphics cards and network interface cards.
All right, we've seen the whole city. Let's step directly inside the processor's office for Section 5, the processing cycle.
This is my absolute favorite metaphor for how the CPU works. The control unit, or CU, acts as the manager or teacher, directing the flow of data and delegating tasks. The arithmetic logic unit, the ALU, is the worker or the student who is actually sitting down and crunching the mathematical and logical numbers. And they do this work on a tiny, high-speed storage space called a register, which functions just like the student's desk.
But before the worker can actually do the math on that tiny desk, the data has to travel. It gets pulled from the slow, non-volatile secondary storage, moves into the much faster main memory, and finally gets loaded into the cache memory. Cache is highly volatile, but it sits right next to the CPU. It holds the most frequently used instructions for lightning-fast access, ensuring the processor never, ever has to sit around waiting for work.
Once the data is close, the machine cycle begins in earnest. It's this continuous three-step dance. First, the control unit fetches the instruction from RAM. Next, it decodes exactly what needs to be done. And finally, it passes that instruction over to the ALU to execute the math or logic, and then the result is safely stored back.
Let's zoom into the micro level of just that fetch phase. It's essentially a high-speed relay race. First, the program counter stores the address of the next instruction and passes it to the memory address register. Then, the program counter immediately updates to the next spot in line. The memory address register sends that address down the bus to main memory, which finally pulls the actual data back onto the data bus and drops it right into the memory data register. It's an incredibly precise, perfectly timed operation.
So now that you understand this incredibly orchestrated dance between the CPU, the buses, and the memory layers, think about the future. As our software demands continue to explode with AI, 4K gaming, massive data processing, which part of this digital factory will become the next big bottleneck? Will it be the speed of our storage, the width of our highway buses, or the sheer core count of our processors? It's definitely something to keep in mind the next time you press that power button. Thanks for joining me on this explainer, and keep exploring.